Hey everyone, we got a real challenging two-part problem here in optimization. It's number 6 in this section. So two parts. First part is we're going to find the dimensions of a box with a square base and with a volume of 216. They don't give us any units, but they would be cubic units. And the minimal surface area. So we want to minimize the surface area of this box. And so I've drew a picture of our box. We've got a square base, right? So the base here, I labeled the side length X. So both sides, all four sides rather, of the base are length X. And then the height of the box I'm calling Y. So the volume of the box we know is 216. What's the volume of a box? It is the base area times the height. Base area is just a square, X times X. So it's X squared times Y. There's our volume constraint, really. So if S is the surface area, we want to minimize that. What is the surface area? Well, there are 6 surfaces on the box. The top and bottom are both squares, so their area is X times X, or X squared. So I've got 2X squared for the top and bottom. The sides, notice they're rectangles. The length, or this dimension, is X, whereas the height is Y. So it's a rectangle. Length times width, or length times height, however you want to think about it, is X times Y. But there's 4 of them, right? So it's 4 times XY. So there is the surface of surface formula. It's a function of 2 variables. I want to get it to be a function of 1 variable. And so I'm going to solve for Y in this case, in the constraint, recognizing the fact that X has to be some positive value here. And so I can replace Y in this formula with this expression. And that's what I've done here. Y is replaced with that. So now I have the surface area as a function of X only. If I multiply 4X times this, I can simplify. One of these X's cancel. 4 times 216, 864. So basically now I am trying to minimize this function for values of X greater than 0. How do we do that? Well, I'm going to find the critical values for this function on this interval, and then do a sign check of my derivative to confirm that I have a minimum. All right, derivative of 2x squared is 4x, and 864 divided by x, remember that is the same thing as 864 times x to the negative 1. So the derivative would be bring the negative 1 down. I get negative 864 x to the subtract 1 negative 2 power. So negative 864 x to the negative 2 is negative 864 divided by x squared. So there's my derivative. This is going to be 0, I hope you see, when 4x is equal to this fraction. When these are equal, their difference will be 0. Multiply by x squared, I get 4x cubed equals 864. Divide both sides by 4, x cubed equals 216. And then take the cube root, right, to solve for x. And the cube root of 216 is just 6. So, do we have a minimum when x is 6? It is a critical point for sure. Makes the derivative 0. Well, we do a sign check of our derivative. When x is 6, we know the derivative is 0. For values less than 6, between 0 and 6, what's the sign? Well, if I plug in 1 in here, I'll get 4 minus 864 divided by 4. 4 minus 864, negative 860. Important part is it's negative. And if I plug in 7 in here, you can do that. You'll get about 10.4. So the derivative is positive. So notice we have a sign change in our derivative from negative to positive. That indicates we have a local minimum at 6, right? Because we're changing from function being decreasing to increasing. And since basically that's the only critical point on this function's domain for all values greater than 0, that's going to be the minimum value. We go down and then we go back up. So at 6, we have a minimum for the surface area. Okay, we want the dimensions in that case, first of all. So we have x. What's y going to be? Remember, y is 216 divided by x squared. So if I plug in 216 divided by 6 squared, which actually gives me 6, then the side of the base is 6 and the height is 6. So what shape are we actually talking about in this case for our box? It's a cube, right? Cube has length, width, and height all equal, and that's exactly what's happened here. To minimize the surface area, the shape is a cube. And the minimum surface area, well, you can plug 6 into our function here for the surface area, and you get 216. And that is the minimum surface area. Okay, so now we'll switch gears to part 2. So that was part 1, and they're going to change things around a little bit. Here we were given information about the volume and asked to minimize surface area. In part B, we're given the information about the surface area. Total surface area is 40 here, and we're going to maximize the volume. Okay, so it's basically still a box that has a square base. And so we've got the same picture up here. And the surface area, remember, was 2x squared plus 4xy. Well, that's going to be 40 in this case. Okay, I'm going to go ahead and solve for y in this case. I'm going to subtract 2x squared from both sides. And then to solve for y, I'm going to divide by 4x. 40 divided by 4x becomes 10 divided by x, right? 40 divided by 4 is 10, and I get 10 divided by x. 2x squared divided by 4x, 2 divided by 4 is 2/4 or a half. X squared divided by x is just x. And this is valid for certainly only values of x greater than 0. Because if x is 0, we would get 0 over here. And actually less than or equal to the square root of 20. How did I get the square root of 20? Well, if y were to go to 0, which means the height of my box gets closer and closer to 0, the extreme case when y is 0, what do we get? We get 2x squared equals 40, or x squared equals 20. So x is the square root of 20. What's going on there? Well, in that case, when y goes to 0, we just have two square pieces of material right on top of each other, and their side length is the square root of 20. Okay, so there is the value of y. Now, what are we trying to do? We're trying to maximize the volume. Remember, the volume is equal to x squared times y. So I'll let v be the volume. X squared times y, it's a function of two variables. Since I've solved for y here now, I'll plug that value of y in. And then we will go ahead and simplify. I'll go ahead and distribute by x squared. And I get x squared times 10 over x is 10x. X squared times 1/2 x is 1/2 x cubed. Okay, I'm just going to keep this an open interval here, which actually I did assign. Well, we'll talk about that later here in a minute. So I'll keep that as an open interval because technically it has to be greater than 0. So actually I should do a sign check on my derivative, and we'll do that to verify I have indeed a maximum volume. So now I want to maximize this function. So how do I do that? I take the derivative. Derivative of 10x is 10. Derivative of 1/2 x cubed, bring the 3 down, I get 3/2 x squared. So this is going to be 0, right, when 3x squared equals 10. And that's going to be true if I multiply both sides by 2/3 when x squared is 20/3, or when x is the square root of 20/3. Now, this is the value they want. They want the exact value. I would probably be happy on a test with, approximating to 2 decimal places. Okay, so 2.58, again, whatever the units are. Now, does that give us a minimum? So I did a checking the value of the function at these endpoints, but really we can't include those. So really I should do a sign check on my derivative here. And I'm looking at values of x greater than 0, of course. And so about 2.58, I'll just say 2.6, about 2.6, we know the derivative is 0. What about values less than 2.6, like 1? Well, if I plug 1 in, I get 10 minus 3/2 times 1. 10 minus 3/2, 10 minus 1.5 is positive. And then something bigger than 2.6, like 3. So 3 squared is 9. I'll get 27 divided by 2, and that is 13.5. 10 minus 13.5 is negative 3.5, so it's negative. So we have a sign change from positive to negative. That means we have a maximum at that point. So that is the maximum value. Now, the value of y in that case, I can plug into this formula here for y, letting x be the square root of 20/3. So 10 divided by square root of 20/3 minus 1/2 x, which is again square root of 20 thirds. Now, this right here magically is equal to just the square root of 20 thirds, which of course means again that both of our length, width, and height of the box are all equal, meaning we have a cube. Okay. And of course, in that case, what's the maximum volume? Well, I can plug in the square root of 20 thirds into our volume function here, right? 10 times that minus 1/2 times that. And doing a little work, I can get it simplified to this. Of course, a quicker way sort of to do this is the fact that the volume is x squared times y. So if I square x, I get 20 thirds times y, which is the square root of 20 thirds, or 20 thirds to the 1/2 power. So I get 20 thirds times 20 thirds to the 1/2 power, multiplied by adding the exponents, and I get 20 thirds to the 3/2 power. So I go through how to simplify this, but really you can just do it that way. Now, getting this expression to equal root 20 divided by 3. I have a little bit of a contention with achieve on that, but let me just show you how I simplified this expression here. So I just rewrite it right here. Y was 10, and I went ahead, since I'm dividing by the square root of 20 over 3, that's the same as multiplying by the reciprocal square root of 3 over 20, right? So there's that part, and then I had minus square root of 1/2. Let's see, what did I have over there? Yeah, 1/2 square root of 20 over 3. So I broke this square root of 20 thirds as square root of 20 over square root of 3 and wrote it that way. Now, the way I would do this is I would first simplify square root of 20 is square root of 4 times 5, which is 2 times square root of 5. So I just replace square root of 20 with 2 times square root of 5. And these simplify. 10 divided by 2 is 5. 2 divided by 2 is 1. So I get these. Now I can combine as 1, and the common denominator is just the square root of 15, right? Square root of 5 times square root of 3. So I multiply top and bottom of this one by square root of 3, right, which I'm multiplying by 1. And I multiply this one by top and bottom by square root of 5, right, which is 1. But then here, 5 square root of 3 times square root of 3 is 3. 3 times 5 is 15. Square root of 5 times 5 is 5. Of course, square root of 5 times square root of 3 is square root of 15. Common denominator, I can now subtract. 15 minus 5 is 10. And then I can rationalize, right, by multiplying by square root of 15 over square root of 15, which is 10 square root of 15 over 15. 10 fifteenths, 2/3. This is the way I would write it, more simplified. They instead write their answer this way. And how do they get that? Well, 2 is the same as the square root of 4. 3 is the square root of 9. Now I can combine this all under one radical. Square root of 4 times square root of 15 is square root of 60. 4 times 15 is 60 over the square root of 9. 69 simplifies down to 20 thirds, and that's how they got it. Of course, that's about 2.58. All right, so a little frustrated with the way Achieve wants those exact values here for your when the volume is maximized, what are the dimensions, and the actual maximum volume, which is about 7.2 cubic units. Okay, so this should be very similar to the problem you're working on. The numbers might be a little different, but I hope this helps on this one.